Swayam Prabha. Digital India. Educated India.
In the last lecture, we have derived the equation relating the components of the external moment acting on a rigid body with the various components of its angular velocities, angular accelerations and inertial properties. What we derived in the last class is that if small x, small y, small z be a set of axes along the directions of the principal axis of this rigid body, so that the products of inertia terms are 0, only the moments of terms of inertia are present, then the moments of inertia of this in the various directions are Ixx, Iyy, Izz. If this object is having an angular momentum L, an angular velocity omega, and then a moment m is applied, the relating equations will be where mx, my, mz are the three components of the externally applied moment on the body. Omega x, omega y, omega z are the three components of the angular velocity, instantaneous angular velocity of the body, and x, y, z are along the principal axis of the rigid body and which are rigidly embedded in the body. What I mean to say, that the frame small x, y, z has the same angular velocity as the rigid body itself. We derive this equation for that. If we now apply this to a simple problem which we encounter in engineering quite often, where a disk that is rotating with an angular velocity omega s about its central axis, which has a mass m and radius r, and if this body is given a rotation about an axis which is perpendicular to this angular spin angular velocity omega s, when this is 90 degrees, then for this motion if this is the motion, then what are the externally applied moments on this? Let us find it out using these Euler's equations. What we will do first, we will attach a frame of reference small x, small y, small z, which is rigidly connected to the body. Now we should remember, since the rigid body is rotating continuously about the x-axis, the location of y and z-axis continuously changes in the space. So what we can say that these are not the instantaneous position of the x and y and z, rather this x, y and z will be the instantaneous axis which is rigidly attached to the body and rotating along with it. At any particular instant, we may assume that this angle is theta, and which is changing. Obviously theta is nothing but, if we assume t to be 0 at this instant when y coincides with y prime, then it is nothing but. Now the inertial properties, from the symmetry we understand that this is one of the principal axis, and any diametral axis will be also a principal axis. So Ixx we call the polar moment of inertia, and for a disk it is something like this. Iyy and Izz are same, equal to half of this. Now let us use these equations and try to find out. So we find that mxx or mx is equal to Ixx omega x dot. Now the angular velocity of the rigid body you have to find out. You see that the rigid body has two angular velocity vectors, one is omega s, other is omega p. So the resultant angular velocity of the body is nothing but the vector addition of this If we now consider I, j and k to be unit vectors along the x, y, z axis, then the components we can divide, or we can actually directly find out the components. What will be omega x? It will be x component of omega s, which is omega s itself, plus x component of omega p. Now since omega p is always at right angles to this, so it will be 0. So omega x is omega s. Omega y. Now if you see the frontal view of the disk, where this is the x-axis, this is the z prime, this is the y prime, this is the x prime, and y and z are the axis rigidly connected to the body. This is theta. We know here that omega p is in this direction. So omega y will have a component of omega p this much, and the component of omega s is 0 because it is at right angles. So this is nothing but omega p sine theta, and the component along the z axis of the angular velocity. Now omega s will have no component along this, and omega p will have this much, which is so these are the angular velocity components along the xyz of the rigid body, and of course small xyz frame is rigidly attached to that. So now omega x dot is this minus I y y minus I z z. Omega y is omega p sin theta and omega z is omega p cos theta. That is the first equation. Second equation, if you use, my is I y y omega y dot now here omega z is omega p cosine theta and omega x is omega s, and m z is and omega x is omega s and omega y is omega p sin theta. So this is the set of equations that will relate the moment or applied moment components along with the acceleration other quantities. Now omega x is omega s, which is constant. That we have to keep in mind. Both magnitudes are constant, not the vector, because this angular velocity vector is changing direction. So magnitude will be constant. Since these are magnitudes only, so therefore this will be 0. Now we also see I y y and I z z are equal, so this also becomes 0. So m x is simply 0. Next, let us see how much we have for the y component. My is now y dot y omega y dot omega p is constant, so it will remain omega p. Differentiate sin theta with time, it will be cosine theta into theta dot, and that is nothing but omega p, and theta dot from here is equal to omega s. It will be omega p, omega s cosine theta. So this we can write I y y omega p omega s cosine theta minus I z z I x omega p omega s cosine theta. And similarly the z component will be I z z. Now from this we get omega z dot is equal to minus omega p omega s sin theta. In a similar way, differentiate this, this is constant, cosine theta if we differentiate is minus sin theta, and theta dot is equal to omega s. So this will be minus So further simplification will lead to this: mx is equal to 0, my is equal to, now Iyy and Izz are same and equal to 1/4 mr square. So the first term will be 1/4 mr square omega p omega s cosine theta minus, now Izz minus Ixx, if you see, it will be simply minus 1/4 mr square. So this minus coming there makes the whole thing again plus, and the first and second term become equal, and you can easily see that and similarly mz is Izz is 1/4 mr square. So the first term is minus 1/4 mr square omega p omega s sine theta. Second term also becomes minus 1/4 mr square omega p omega s sine theta. So the whole thing becomes so the interesting thing is this, that my and mz, the magnitude is same, one is cosine theta, one is sine theta, and we know that such a thing represents a vector. That means its total, these two can lead to a vector which is along this direction. This is half m r square omega p omega s. Its component along y is half m r square omega p omega s cosine theta, and its component along this is obviously a negative quantity because it is opposite to the positive direction of a z, and that is half m r square omega p omega s. So therefore we find that the torque which must be acting on this has to be along y prime axis and will be this. So this is the moment vector whose magnitude is half mr square omega s omega p, and this acts along the y prime axis. So you see, it is something counterintuitive when you consider our dynamics of planar system, where you apply a moment, the thing tries to accelerate in the same direction. Here what is happening, the body is spinning like this, you are trying to rotate about this. You don't have to apply moment in this direction. Moment which you will have to apply will be in this direction. So if it is spinning like this and I am trying to rotate the disc like this, I have to apply a moment in a direction which is normal to the direction of rotation. There is a standard, in such simplistic situation, there is a standard way to find out the position of these three. This is called the spin axis or spin vector. This is the precession vector, because such motions where the spinning axis of a rigid body also moves or rotates, that rotation is called precession, and that's why we call it precessional motion. So this is the precessional velocity vector. Then if you rotate the spin vector by 90 degrees in the direction of precession, that is this, it will coincide with the moment vector, and this moment is the moment which has to be applied to produce this motion, that you have to keep in mind. So this is something very strange. When a body is spinning and rotating, if I apply a moment in this direction, it will rotate in a direction which is at right angles. We can get a clearer picture of this in a simplistic approach, and we can explain this in this manner. So this is the flywheel or disc, whatever we may say, which is spinning in this direction. And if that is so, if you take a plan view, you can show this as the disk, and this is the spin vector. When this is a large spin, so we can also say that this happens to be the angular momentum vector also, which is equal to moment of inertia in this direction, that is half mr square into omega s. That is the angular momentum vector of this. Now I am giving a rotation to this about this axis. So that means I am giving a rotation about this with a velocity omega p. So in time delta t, the whole thing will come somewhere here. This is the new angular momentum vector, and this angle will be how much? The angular velocity, which is omega p, into the time, which is delta t. So this is nothing but omega p into delta t, this angle. What is this? This is the change in angular momentum, because original angular momentum plus the change makes the new angular momentum. So this is the change in angular momentum. And how much is this? The magnitude of this is this length into this angle. This length is L, and this angle is omega p delta t. So the quantity delta L by delta t tending to 0 becomes L into magnitude, I mean to say, omega p, and L is nothing but the moment of inertia of the disk into omega s is the angular momentum, and that is equal to half mr square. And in which direction? Now we know that angular momentum vector, rate of change of that is same as this. So this being the change in angular momentum, the rate of change of angular momentum vector will be in this direction, and that tells us that this will have to be also the moment vector matching with this. So this is the moment vector, and its magnitude is this, what we found out from the exact analysis of the whole thing, or direct analysis of this using Euler's equation. So this has an important consequence for engineering systems, because we have many cases where we have a spinning or high speed rotating disk or rotor or a body, and which again is forced to turn its axis or its orientation because of the motion. So for example, the turbine in say a jet engine. So there I think the body of the plane contains the turbine rotor, which is simply represent like this. So this is the turbine rotor supported by bearings. Let the distance between the bearings be the moment of inertia about the central axis is I, or we call it polar moment of inertia, and its speed be omega s. Now suppose now the whole thing which is, so this is taking a turn, the velocity v and the radius of curvature r. The whole thing is taking a curve, a turn towards right or towards left. So what will be the bearing reactions? When it is going straight, the only thing the bearing will have to support is the two parts of the weight. The weight is supported. If it is exactly at the center, then this is going to be total weight by 2. This will be also total weight by 2. Now since it is taking a turn like this, the whole axis of this rotational axis of the rigid rotor is taking a turn in this direction. Now how much will be the precessional angular velocity? That means what will be the rate at which it is rotating towards this? It will be same thing as the speed at which it is traversing the distance divided by r. So omega p in this case, that means the amount of rotation of this, suppose if it is here, this is the axis of spin, and after some time delta t, the axis of rotation is this, because it has to be always at 90 degrees. So this amount of rotation will be same as this. Now in time delta t, if it has rotated this much, so this will be delta t into omega p, if omega p be the rate at which it is changing its orientation. And we know that this is nothing but this length, which is velocity into delta t when delta t is small, divided by this radius, that is delta phi. Delta phi into r is this arc length, and in this small limiting case this is nothing but v into delta t. So delta phi by delta t is nothing but v by r, and delta t by delta phi is actually, we have seen, omega p. So omega p is nothing but the velocity of this plane, of this moving object vehicle, divided by the radius of its turn. And since it is rotating towards right in this view, if this is omega s, omega p will be up or down? It will be down. And this is omega s. So we have seen that if you rotate the spin axis in the direction of precession by 90 degrees, you get the torque direction. So if you rotate the spin axis by 90 degrees in the direction of precession, you get the moment vector direction. So moment vector will be this. That is, this is the moment which must be applied on the body to produce this motion. Now, how a body can be subjected to an outside moment? In this particular case, the only place where it can get some external force or moment is from the bearings. So, on the shaft of this rotor, there must be forces whose resultant effect on this body will be a moment in this direction, and therefore a force has to act here and an equal and opposite force has to act here in such a way that the moment of this force, which is F into L, is equal to m. And the magnitude of this moment also we know from our analysis. It is moment of inertia of this rotor I into omega s into omega p. And the direction of the two forces, which are equal and opposite on the shaft, will be depending on the direction of rotation, the turn. So therefore the resultant reaction on the rotor shaft is going to be now different in different location. Here it is going to be W by 2 if it is symmetrically placed plus F. F is equal to I omega s omega p by L, and here you can see that it will, this force is going to cause a reduction in this. So resultant force here will be W by 2 minus I omega s omega p by L. So therefore the bearing reactions will be depending now on this particular effect, and this effect, that a rotating or spinning body, when its axis of rotation is given a precessional motion, a moment has to be applied in a direction which is at mutually perpendicular direction, is called a gyroscopic action or gyroscopic effect. So as a simple case, we have seen here the gyroscopic action leads to alteration of the bearing reactions, and this must be taken into account while designing the system. If we consider that the bearings are subjected to only W by 2, that is the weight, we will be wrong, because one of the bearings is going to subject it to a much more load than what simple weight will result in. This can be also used effectively sometimes. One very popular usage of this is the crusher, where this effect is effectively utilized. So if we take a crushing machine, this is the crusher. It's a simple configuration I am taking, where the radius of the crusher is R, this distance of the median of the crushing disc is capital R, and in this particular case let this be 90 degrees. Mass of this crusher be m. So what we expect is, and this is hinged here, what we expect here is that the total force here acting is on this, the total force will be simply the weight of this, if we ignore the weight of the arms, etc. So if the weight of the disc is W, then the reaction between this floor of the crusher and the roller, the crushing roller, will be simply W. So this weight will be just balanced by this, and the crushing force will be W. So if we call a 10-ton crusher, it means that the roller has a 10-ton weight, and it can produce a total crushing force at the contact point below W. Now, but let's see that what happens if this whole thing is rotating in this direction in angular velocity omega. If we assume that there is no slip, which is quite practical, then what will happen? This will rotate in this direction. That means it will have an angular velocity or spin velocity in this direction, and without considering any slip here, this can be found out from this simple relation. That is, if this point is moving with a velocity omega into r, and if this point's velocity is 0 because it is in contact with the floor, and then again to produce the same velocity here, it must rotate with an angular velocity omega s, and this distance is r. So omega s, or the spin velocity, will be this, which will generate some angular momentum of this heavy roller. At the same time, we find that its orientation is changing with the same angular velocity omega. So if it is now here, after some time it will be like this, it is like this, after some time it will be like this. So this whole plane of the disk, or the axis about which it is spinning, is rotating with this angular velocity. So omega p, or precessional velocity, will be simply omega. Now if we assume this to be a disk, then its moment of inertia will be W by G is the mass, half r square, half mr square is the moment of inertia. So we know now that this is omega s, this is omega p. Then we know that torque must be acting in this direction on the system. That means there must be a torque which is acting on this body, and according to our thing, if you rotate the spin vector by 90 degrees, so it will be coming out of this board. Now let us see how this can be given a moment in this direction. Moment in this direction means an extra force in this direction, in such a way that this distance being r, F into r is the moment, which is omega into omega s is the moment, and that is equal to F into r. So the moment which here, the total moment which must be acting on this is W into r minus F into r. Sorry, I should change it. Total moment acting on this is W in the downward direction due to gravity to r minus reaction F into r. Now this F, that means the force it is receiving from the contact at the floor, is the crushing force. So this is the crushing force. So what I have been telling just now is that this is the magnitude of the gyroscopic moment which must act on this to have this motion, that angular spin in this direction, and a precessional motion in this direction. And following the condition as you have mentioned earlier, the moment must be acting along this. That means about an axis like this. Now to produce that, so therefore this force multiplied by r can produce a moment in this direction, F into r, but the gravity will produce an opposite moment, minus W into r. So this will be the total moment acting on this roller system, and F is nothing but the resultant force of contact between the floor of the crusher and the roller of the crusher, or effectively this is the crushing force. So the crushing force which you will get from this is equal to, this relation gives us W plus half r square omega s by g r into W. I divide both sides by r and take w to this side, or this can be written as w into 1 plus. Now omega s is simply this, so omega square r square r by g r r w, sorry, w is not there. So omega s we have written as this. So this gets cancelled and finally we get w into 1 plus omega square r by g. So we find that resultant crushing force is more than the weight. That means the gyroscopic effect here has helped to produce a crushing force which is more than the weight of the roller, which normally we expect to be the crushing force. And the magnitude of the increase, it depends on the speed. For a higher angular speed, we find that we can generate a higher crushing force without increasing the weight of the roller. So maybe a 10-ton roller can produce a 15-ton crushing force. So this is an advantage we get. So this kind of an effect, that means the forces or bearing reactions or moments which all get generated because of the gyroscopic action must be taken into account, and whenever a rotating body changes the axis of rotation is changing, there the gyroscopic action will come into action. So there are many examples where you will find that like a flywheel of a car, it is quite heavy and it is rotating at a high speed. So when the car is taking a turn, the gyroscopic action will change the bearing reactions, and that excess force which gets generated due to the gyroscopic action needs to be taken into account while designing the system. Sometimes the situation is a bit more complicated. Now for very symmetric bodies like discs, rotors, it is fine, but sometimes we have not perfectly symmetric bodies, like say a propeller of a plane. Propeller of a plane is not perfectly symmetric though it has an axis of symmetry. In such cases it can be shown that the gyroscopic action is not a static force but it is a dynamic force, and that frequency of that variation of the gyroscopic action is related to the spin or the rotational speed of the propeller, which is normally very high. So in such cases what will happen, that the bearing reaction will no longer be a static force like this, but will be subjected to an extra component or extra gyroscopic action, which is again vibrating or changing with time. That means it is changing, fluctuating between a maximum and minimum with this frequency with which the unsymmetrical body is rotating. And there the problem is more serious because it can generate very dangerous vibration of the system and leading to fatigue failure. So I think there are many examples in machines where whenever we find that a rotating body is changing its axis of rotation's direction, we have to be careful, we have to consider the gyroscopic action into picture and calculate the various forces which get generated due to this.